actually 9:01. We start, right?
Huh?
It's 9:01, so we start?
Yep.
I think we start.
Yeah.
Good, okay. So we're going to start. Welcome, everybody. Today is the Louis big day for the next 2 hours, the next two big hours, right? It's always that point you need to get to with a doctoral degree. You do all this work, and then at some point, it's that moment of, defense, which is great. So we have Stephanie Müller here from MIT, who's been on the committee, and of course Panos Michalatos, well known to everyone. And might be more people will be coming in. Jose Luis has been with us for a little bit. He did an MDiv, he then took a leave, which is a legitimate thing, and came back for more. And he is now at the conclusion of that more phase. And this is really about you, so we'll turn it over to you. The process will be about 30 to 35 minutes of presentation. Then the committee members will have some questions, and then we'll open it up to all of you. And then you will all be sent out, including Jose Luis will deliberate what the outcome, call him in, and tell him what the outcome is, and then that's going to be basically the end of the proceedings. Okay? All right, very good. Thank you very much for coming.
All right. This is it.
It is.
Good morning, everyone. My name is Jose Luis. Many of you know me already. I see a lot of familiar faces. Thank you very much for coming and for joining us today. I also see many familiar faces who, some of you have been working with or using this project that I've been working on for the past 2 years called Máquina, right? And for many of us, it's basically this like Grasshopper plugin, Dynamo plugin, or this like interface that you use to like move the robot around and do fancy stuff. But today, because this is doctoral defense, I would like to indulge a little bit and invite you guys to join me in that moment on reflecting on some of the ideas and some of the high-level goals that went into that project, some of the background and the cognitive science that is behind the decisions that I took when putting this together, and especially how I believe those could change in the future the way we interact with robots, the way we program them, and the way we work with them, right? And that's what I've come to name Enactive Robotics. And today I will be presenting a model, an action state model for concurrent machine control, okay? That is a mouthful, I understand, but I will use these 30 minutes today to unfold what I mean with some of those terms, all right, as part of this presentation, which is the last day of my doctoral studies here today, all right? Oh, water, that's great. So let me start by the beginning and by stating some of the problems that I see today in how we use machines, how we program them, specifically for industrial robots. And a lot of these concerns come from my personal experience when teaching. I've taught a lot of workshops, a lot of courses dealing with robotics. And to no surprise, it is hard. People find it hard to learn about robots. People find it hard to learn how to program them. And my take is that it's not their fault. There is something about how we teach and how we learn robots that is not right. And that's what I would like to address with this presentation. And the first thing is that machines, robots, and fabrication machines, they require someone to be able to write something like this. This is a very simple program for ABB robots in rapid language. And no surprise, this is absolutely unintelligible. It requires knowledge from inverse kinematics, forward kinematics, spatial transformations, and nobody who just wants to use a robot and tinker a little bit with it and make something should be exposed to this kind of logic, all right? It also doesn't help that industrial robotic arms, the languages that they run, they're not standardized. So this particular one here is for ABB robots, but the same one here is for universal robots, and the exact same program here partially is for KUKA robots. So learning how to program a robot is also vendor specific. It depends on which kind of robot you're using, and that knowledge is barely transferable between machines, all right? For a program whose human representation will be something like this, all right? Many people in the field have tried to address this issue. And in the past few years, there's been a myriad of, for example, Grasshopper plugins trying to address the idea of programming robots. So one of the most popular ones is HAL by Thibaut Schwartz. And it's a really good tool. It's a very powerful tool. But my take with this kind of approaches is that if you see the components and the namings, they do require that you get your mind closer to the machine and that you learn the specifics of how things are implemented in machine terms, rather than bringing that process closer to the human mind and making programming closer to how I think about moving a robot around, all right? I very recently read this PhD dissertation by Nadia Pick, Machines That Make, and very interestingly, she had a chapter where she describes this failed situation about these MIT students who wanted to make this fabrication with hot blade, and because system integration between robots and other devices is so tedious as well, they failed, and they had to have a human on the loop manually tweaking the temperature of the hot blade while it was cutting, not integrated in the robotic system, all right? And this is MIT students. It's very high up the ladder, you know? So if they couldn't figure it out, we may have a problem here, all right? Also, I'm very critical about what I would like to define, and I will talk about this today a lot, about what I would like to define as the offline programming model. Who has ever 3D printed anything here? So all of you are acquainted with the process where if I want to 3D print something first, I have this software, this modeling software where I model the thing, that's one platform. Then I have to move that model to somewhere else where I slice it and I get all the G code. Then I have to move that to somewhere else, which is where I actually 3D print the object, and then I get the object. This transmission between platforms prevents experimentations, prevents iteration, prevents fluidity in this creative process, right? And if something goes wrong, you have to go all the way to the beginning and start over again, right? This process is very unidirectional, and it doesn't allow for a back and forth between the creator and its tools, which comes from a very long tradition of craftsmanship, where the wholeness of the creator, the tool, and the material is an integral part of this creative process. And many authors have argued that that craftsmanship is a little lost. And it's lost because of the bias of how these machines force us to use them and to make things with them, all right? So there's all this new wave of interactive fabrication where there is a claim about whether if we close back the loop and whether if we make these machines accept back and forth, right? And a lot of work has gone in that direction as well. There are many projects that deal with personal fabrication, like for example, Constructable here on the left, or Roma here on the right, where users were given an interface where they could interact dynamically back and forth with the machine that was making things for them, all right? The problem with this is that the tools that enabled this were very specific, very customized to these particular projects, and were created by people with very high skills. In order to do this, you have to hack a lot of things, and only people who really know what they're doing can do that. It's not accessible, it's not open to wider audiences, all right? And it's a shame because there is a tradition about wanting to use robots and fabrication machines in creative fields, in design, in art. Here we have Mimus by Madeleine Gannon, we have Mimic by Design.io, and like the classic Alexander McQueen cat show in spring, summer 1999, all right? So all of these tools, it's happening. People are willing to use these machines for uses outside engineering and manufacturing, yet the tools required to make this happen are very specific to the use, and there is no systematic, no open way of making this happen, all right? On top of that, this offline unidirectional programming paradigm has another problem, and it's a cognitive problem, okay? The problem is if I have to pre-embed all these decisions before making anything, I have to be really smart about thinking about all the possibilities, embedding them into a program that is going to run in the machine, all right? How can I be trained and be good at making all these decisions beforehand if I have not yet been exposed to the machine, if I cannot touch it or use it? It's like a conundrum. It's like an egg and chicken problem, right? And very often the solution to that problem is what I would like to refer as abstract training, all right? If you want to learn robotics, the first thing you're exposed to is like a whole lot of math and physics. This is based on a real story. This was me 4 years ago taking a class with Professor Wood in robotics at the engineering school. And this is me trying to catch up with the math of the class because she just could not keep up, all right? And I'm a huge nerd. Like, I really like math, you know? So it's tedious. It's very involved. And this is great for people who want profound and long-lasting knowledge in robotics. But for people who just want to get the trick done, this is probably not the right way to start, right? What is the right way? I don't know, but I think it's a bit closer to this. I don't know if it's children. I don't know if it's like, but I think there has to be an alternative way to approaching robots that doesn't come from symbolic training, but it comes from somewhere else, from interactivity, from practice, from action. We're going to get to that very soon, all right? And why do I think that? Because I think that if robots are moving from highly industrialized environments to more research, lab, to creative audiences, there have to be different tools that address each one of these particular fields, all right? That's my take here. No questions, okay. So, yeah, thank you. So this is what I see the problem space, okay? And what I would like to contribute to this problem space is, and my contribution to this problem space comes from a long and wide wealth of studies in the cognitive science throughout the 20th century, all right? All this situation that I'm describing was very similar in the 70s with computers. People didn't know how to use them. It was very tedious. It was only accessible to like a very, very elite. But now they're everywhere, right? And I think that that process is happening with robots as well. There were a lot of people in the 70s and the 20th century who studied the cognitive aspect of how do we learn about using and interacting with machines, all right? And my three main pillars in this dissertation have been Jean Piaget, who founded the theory of constructivism, a theory that says that how we learn things is by creating models about what we want to learn and then comparing those models with reality, all right? One of his disciples, Seymour Papert, he was a pioneer in the field of computer science and mathematics, but especially in the cognitive aspects of children and using computers as an aid to education, all right? He was the founder of the Logo project and this like turtle that moves around and draws on a paper, and his work is like tremendous. You should read his books. He's amazing. But today I will focus a bit more on this gentleman here, Jerome Bruner. He inherited from this lineage of cognitive science, but his approach was towards building a generic theory of instruction on education, all right? And it's very important. I'm going to pause a little here. It's very important because his main contribution was the idea that when we learn about the world, specifically when we're kids, we learn in 3 stages. And the first stage is what he defined as enactive learning. Enactive learning is through embodied cognitive interaction, and it's through what he describes as action. Action is when we interact with our environment, when we interact with an object, when we interact with each other, and it's through that interaction and the effect that that action has on our environment that we perceive and that we understand that environment. The reality is not something that is abstract out there. We have to interact with reality in order to apprehend it. That was his take. The idea of enactive learning leads to the second stage, which is iconic learning, which is when we have so much understanding through action that we can abstract some of those ideas and understand them through through visual representations. Like an image of a car gives us an understanding of a car because we've had experiences with cars before, all right? And further development in iconic learning leads to symbolic learning, which is the ability to be able to abstract that knowledge into symbols and concepts and communicate with each other with, for example, language, which is a very symbolic environment, right? That was his take on how do we learn about the world around us. And he was very clear about pointing out that this is the direction. We start with action, which leads to images, which ends up in symbols, in reason, right? And when I read about these theories, it was very eye-opening, because for me, this represented what I believe was wrong in the way we learn about machines and robots, which is that we basically do it the exact other way around. We start with symbolic training, which perhaps leads us to understanding a robot, and then a month later, maybe we are actually touching the robot and doing something with it, all right? Which for me is a very, very lost opportunity. It's a lost affordance, because as Seamus Papert would say, the tangibility, the physicality of a robot as compared to a computer, which is a very more abstract environment, the physicality of a robot is a very, very suitable framework for what he used to call object to think with. All right? So, where is this leading us? It's leading us to today, and what I would like to refer as enactive robotics. Okay? Enactive robotics is a model that I'm presenting here today, and it's a model, it's an action state model, and I will define very soon what that means by action state model. And it's an action state model for the design of systems for concurrent machine control. Okay? What do I mean with this? The objective of this dissertation is to define a conceptual model, a set of guidelines, principles, not for the design of robotic systems, but for the design of tools to create robotic systems, all right? So the outcome of this dissertation would not be, this is a set of principles for a Grasshopper plugin. No, it's a set of principles for designing Grasshopper plugins or programming languages or any digital environment geared towards programming or controlling a robot. It's a level up, all right? That's why, please bear with me. I'm gonna get a little abstract and conceptual for the next 5 minutes, but we're gonna go back to the practicalities of what this means, all right? And my main goal here today is to defend that this model has two main advantages, all right? One is that it makes learning about how to use machines and robots much easier. But also, that once you're there, it also provides a wider and a deeper spectrum of possibilities as compared to the typical models that we use today, which is offline programming, for example. All right? We all good? All right. So let me break down a little bit what I define by offline modeling, offline programming, all right? And I'm going to pause here a little bit because I'm going to be using a lot of diagrams with this very same language. So I would like to describe that when we use a 3D printer, for example, there's three main parts, right? There is some kind of agent. So here is usually a human, and it's the programmer, which I'm representing here in blue, right? It's the person who makes decisions, right? That person interfaces with some kind of digital environment, which I'm representing here in orange, all right? And that digital environment is the mediator between the decision-making and the CAD, the geometry, and turning that into some kind of robotic programming, right? Some file. G-code, rapid, you name it, all right? That is the programming environment, all right? However, at some point, that file gets into the machine, you put it on a thumb drive, you run it, all right? And then there is, here represented in green, is the mechanical aspect. It takes the file, there's a controller system, and that controller system uses back and forth communication with the actual like rotors and motors, etc., to drive the machine according to that program, all right? This is the gap, the defer gap, and this is the two different systems, the programming system and the execution system, the control system, all right? You probably see where I'm going with this. This duality, this split, is what I believe is not being helpful for us to push forward the agenda of using robots and making things with them, right? So what I propose here is blurring the line between those two systems, right? And integrating them together into a system where programs are not designed and then executed, but programs are enacted, all right? And that in action, I define it as the act of having a decision-making agent that can interface with a central state representation through actions dynamically while the program is being executed, all right? I'm going to unfold this in a second. So what is the three main parts that this model is based on? It relies on three main foundations. First is the fact that you need to have on your system some kind of decision-making agent, because all the decisions are not pre-embedded in the program anymore. You need to have somebody, a human, a neural network, maybe an algorithm, that's fine, but somebody who can make decisions, who can take data, process that data, and turn it back into some other data, all right? And that agent has to be that agent has to be connected to the system in real time. This has to be able to happen back and forth, all right? That agent has to have the ability to interact with the system through what I call actions. And actions are based on the enactive learning paradigm, and actions are the basic cognitive unit of interaction with the system, all right? We interface, we relate through actions, all right? And actions have a set of properties. First, they are self-contained. The action contains all the information that it needs to convey, whatever that action wants to do, but knows nothing else about the entire system. It doesn't depend on the machine. It doesn't depend on anything else. It's platform agnostic. Actions are not dependent on a particular machine. They're generic. And whether if that action can or cannot be applied to a particular device, that's a different story, all right? But the action doesn't care about that. They're universal. They can be applied to many different machines or not. And they are contextual, which means that the effect that they have depends on the state of the machine at that point. If I say move up, the final location is going to depend on where the machine was before, right? And they are sequential, and this is important. Whenever I request a lot of actions, they do have to happen at the sequence that I requested them, all right? And then the third pillar of this model is what I would like to refer to as the state representation. This model is based on the centrality of some framework that I call the state representation, which mirrors the state of all the agents that are involved in this system, all right? The most important function of this state representation is to be the mediator between them, okay? What does that mean? For example, if an agent says, can you move 100 millimeters in X? The action is platform agnostic. It doesn't know which machine is going to, but the state does. So if the state says, well, this is going to be through the 3D printer, then that action can go directly into the 3D printer because 3D printers accept relative motion, all right? However, if this action is going to be applied to an industrial robotic arm, then the state representation has to turn that into something that conveys that movement, but it has to add a lot of extra information because there's like 6 degrees of freedom, there's like speeds, whatever, so it has to fill in the gaps that we're missing. And on top of that, the state representation, if this is going to go to an Arduino board, Arduino's boards cannot move anywhere. So the state representation is the one that says like, oh, this action is not valid for that particular machine, all right? Is this clear? What are the properties of the state representation? It's mutable. It has to be able to change dynamically over time. It's asynchronous. Its execution cycle does not depend on any other machine. It's independent. It's autonomous in that sense. It's the mediator. Everything that happens between a machine and the decision-making agent goes through the state representation. And it's transparent because any agent has to be able at any time to query, to ask the state representation, hey, what's going on in the system, and get a response back, okay? That is important to make back and forth decisions. All right, that was the abstract part, okay? So how does that turn into something tangible that we can use? So as part of this dissertation, I developed what I call the Robot Ex Machina framework, which is a technical implementation. It's a sample of this model applied to industrial robotic arms. Okay, why? Because I happen to have a lot of those around my environment, but also because I see them as being very close to like an all-purpose fabrication machine of sorts, because they have so many degrees of freedom. So it's kind of like a nice platform to express these ideas. Okay, and the first thing that I would like to present is this. We can think of this framework as sort of like a small programming language of sorts. It's not really like that. But it's a small programming language with English verbs that denote action coming from the model, right? There's no rope target, joint target, whatever, like, there's no like robot language, there's human language, all right? And one of the characteristics that makes this different from other similar systems is that this system accepts both actions in relative form, so move up from whatever you were, or actions in absolute form. Move to this X, Y, Z coordinate, all right? Why is this possible? Because we have a state model that gives me information about where the machine was before, so I can do relative motion, all right? But this is not a programming language in itself, because it's a big pain in the ass to implement those things. So I started by implementing this in the C# in the .NET environment, okay? So this is what a program in the Machina language would look like with some of this additional C# language that it needs to run on, okay? This is the architecture of the system. I'm not going to go into detail. Probably 80% of the technical work that went into development here went into this core library, but the technicalities are not important. However, you see that the architecture mimics the model that I have described. There's like an input language. There's like some technical something that takes care of making everything, and then the model is extensible by subclassing certain classes to any particular device that we want to control, okay? And there's also information that is coming back to the decision-making agent about changes in the state of the system, all right? Which means that if I wanted to write a small program in the Machina language, I can just add a tiny bit of extra code to make it C# compatible, and that can compile, for example, offline. It can compile to Rapid Code, to Universal Robots, and for KUKA, the exact same program. It's actually very easy to do, all right? However, what's interesting is that this framework allows this real-time concurrent communication, back and forth, right? I'm also not going to describe the architecture of that, but what's interesting is that whenever an action happens, there are many stages in the execution of that action and many notifications that go back to the user, which is how this system provides an environment that fosters reactive programming rather than imperative programming, all right? So early tests of this framework proved successful. You could do like interactive real-time control of machines, and it was actually a lot of fun, okay? But these early tests also proved that C# programming is a very niche thing. It's only accessible to like a very tiny group of people who are somehow super users, and building Windows apps is not something that everybody can do, all right? So there was a need to make this available to a wider audience, this creative audience that I'm trying to address here in this dissertation. So obviously, what those people usually use is visual programming languages. So very immediately, we ported all this logic to Grasshopper as a Grasshopper plugin, and we also ported it as a Dynamo Beam package, okay? So you can access the exact same functionality, but from a visual programming environment. The problem with this was very simple. Visual programming languages, the way they work, they start somewhere, they produce data, and they stop. The real-time aspect is actually really hard to implement natively in Grasshopper or Dynamo, right? Because of the way they work. So we can impose actions, but getting data back is really hard. And if we stop there, then we would be perpetuating this model that I want to break free from, that I hear, right? So while this was happening, my friend Nono and I were preparing for this workshop, and we had all this like debate about like, oh, we're going to do a workshop with robots and machine learning, but we really don't know who's going to participate. We don't know their skills. We don't know which languages they use. We don't know what tools to provide for them. So what should we do? Should we like rewrite Machina for Python and JavaScript and all these languages? This is going to be super tedious. It's going to take forever. It was a big problem. We didn't really know how to address the uncertainty of a group of users that we didn't know, which was it's actually like a very legit question for a doctoral research as well, right? So we had a sort of aha moment here, and we decided, well, what if we, from this model, what if we could isolate in a self-contained environment all the part that was technically complex to implement, all this like state representation, the back and forth, low-level communication with the machine. What if we pack that in one single environment? Very simple. And then we provide somehow access from any programming language, any platform, any environment to any other decision-making agent. And we make the back and forth communication very simple with a standard protocol that we chose to be WebSocket. WebSocket is super easy to implement, and it's available in most programming languages that I'm aware of, all right? So that led to what I'm calling here the Machina bridge. It's a really simple, really clunky, really ugly interface, all right? that basically has three main parts. The connection part, a command line interface where you can type machina actions, and then a visual representation of the queue of what's pending to be executed. And the way you interact with it is very simple. You have a robot, right? And then you have this command line interface where you type, can you move somewhere? And as you hit enter, the robot starts moving. And all the actions that you issue, they start going into this queue, and they start executing sequentially one after the other. All right? So that was the way to access the robot. But what's interesting is that this interface in the back end has a server, a WebSocket server, that allows any other application from your computer to connect from the back, all right, and send string actions back and forth and get notifications back as well. Which means that now we did not have to replicate any of this code for other platforms, but just by creating like a very thin layer for example, processing or Python or JavaScript, which basically just turns these actions into a string that gets sent to the bridge and received back, we could basically extend this model to any conceivable framework by only creating like a very thin layer of code for each one of them, which was really nice. And it actually worked pretty good because like right now we have the main core library, we have this command line interface as the bridge, but we have Machina available for Grasshopper, for Dynamo, but also for processing JavaScript, Python, and virtually any other language that you can think of. It takes like 50 lines of code to add this functionality to any other environment. It's actually really nice. And everything is open source. Everything is available for free. No, and can be hacked, and can be changed, and can be adapted. I would like to go back to this idea of, circle back to the idea of the bridge as not only as a very useful tool, but something that we found along the way is that the model, the interaction model that the bridge provided, all of a sudden was really interesting because instead of having someone sit and give them like robotic knowledge for 2 hours before they could write like a very simple program and run it, all of a sudden that changed. And then all of our participants were like, oh, open this thing, connect to the robot, and start sending, move somewhere. And the smile that somebody gets as they type the first action and they see the robot moving, that has no value. That is, for me, is the game changer that made things really valuable. And I've seen reports, I've been hearing about all these people changing the curriculum and starting to teach robots by using the robot and then building up to the complexity and all the logics that are behind it. And I will get back to this idea as soon as I describe the control user study. All right? Okay, so enough with the boring stuff. Let's see some of the work that people have done with the whole Machina environment. All right? And a lot of this work started with a class that my advisor, Professor Betchwell, and I started in the fall of 2017. It was a digital fabrication class in which many students ended up using robots and ceramics for projects that, that try to engage and innovate in how we understand digital fabrication and clay. All right? But at that time, the framework was still not very developed, so many of these students had to resort to the classic offline paradigm, all right? With one exception. There was a group of students, Soliman, Francisco, and Hyunji, who created this like 3D printing lattice system that relied on a self-calibration cycle to recalibrate for the deflection and the changes that happen in fresh clay as you deposit it, right? So they were able to push this project further and implement a closed feedback loop system where they could 3D print a layer, measure that layer with a 3D scanner, and then incorporate the deflection of those layers back into the system. And then they ended up creating this last Christmas, this like massive 3D print. It's like this big, it's on the 3rd floor. You should really check it out, it's really cool. We're gonna put some pots on it, right, Janissa? You're on it, right? But that was possible because like the whole system allowed them to get information back from the robot, which was fed back into the Arduino board, and which was taken by the algorithm that was driving the whole 3D printing process, all right? Similarly, what if we could 3D print in real time? What if while the 3D print was going on, we had a digital interface that allowed us to change the shape of that 3D print, but also, because the system knows what's going on, with the 3D print, it will constrain the freedom that we have so that we didn't create like things that fell off or broke, et cetera, right? So this was a prototype that I created like last year, where I have an interface where I can model while the thing is printing. I get feedback from the digital interface. I get feedback from the physical print. And I was able to create this like real-time modeling environment, like a modern version of a throwing wheel, all right? And again, that was possible because there was a full closed feedback loop between me, the script that I was using to model, and the whole Enactive system. I did some work with some students at the Build Space this summer, where they were using robotic hot wire cutting, all right? We connected it to an Xbox controller, and we were able to drive the foam cutting with the Xbox controller, which eventually led to the project that they did, where they used this foam cutting system to create this like very large inhabitable pod. Also, Hakim Hassan from the Build Space, who's also here today, he's one of the one of the earliest adopters of this whole system and one of the most patient ones as well. He very recently created this pavilion for the Green Build conference in Chicago, which was going on in November. And he used Machina to create a full rig where 2x4s were picked up from a pile. They were put on this jig, then there was like a saw that was chopping them to measure. It was put on the final thing, and then there was like a nail gun that would like assemble everything together modularly, right? Even though this project was implemented with full offline system, it showcases the capacity of the framework to be not only experimental and novel, but also to be like a robust, resilient production tool for very fast, very powerful robotics, right? And it's also really badass, right? Like saws and like nail guns. It's like America in a nutshell, huh? If only there was like a flamethrower somewhere, huh? Yeah, ended up in this prototype that was built with robots in the marketing material, right? But building on top of this idea, some other of my colleagues at the Build Space, so Ardavan, Mehmet, and Sepki, they're trying to address a similar issue, but in this case, they were trying to address the issue of uncertainty on a construction site. So they were able to implement computer vision to figure out where certain elements in an uncalibrated environment were, pick them up, put them on the jig, and then be able to assemble them to measure, all right? By closing the system with camera, computer system, and feeding that back into the main algorithm. I know. But what if instead of algorithms, things were driven by humans, systematically on the loop, right? So in this prototype, my colleagues and I were trying to figure out how would we create like a large-scale construction. Very simple, just 2x4s, balloon frame, but on top of a baseline construction system where the robot is using power and precision, there was the possibility for humans to intervene in that process and make small tweaks. Whether if that was to counteract for calibration issues, or whether if what that was to apply design decisions, to make decisions back on the fly, right? So this idea of like integrating robots and humans collaboratively on the construction site all of a sudden became much more relevant and possible because the system is open to real-time intervention by humans. So here we were able at the ETH Zurich to build this small pavilion with our workshop participants. It was a Saha design. I believe it's the first Saha design that has been fully built by robots, all right? With this system that was a hybrid between robots doing all the precision work and humans making small tweaks, all right? Provided by the possibility that the system could drive the two robots, and then there was like a lot of feedback between users, scripts, et cetera, et cetera. Carnegie Mellon students were able to create this interactive installation to move this board around and have the robot project an overlay of anatomical images on top. Not everything is building or making things, but like there's like softer ways of doing that. We were able to create, for example, installations for Kids Day at Autodesk, where we had this screen where kids could draw, and then drawings would be sent to the machine and printed. We were able to do that on a closed feedback system. But we could add more to that. So we also, in this example, we incorporated a neural network, SketchRNN, that was published recently by Google. And what the system does is like you give it an initial input like this, and then the neural network fills in with the rest of the sketch. So what you're seeing here on black is what the user input, and what you're seeing in blue is what the machine learning framework is providing. So it's like this sort of like collaborative drawing between humans, robots, and machine learning, right? Which was further extended by a colleague of us, Sean, who thought, well, what if we created an art installation where we use this system, but instead of giving it input constantly, we used the last stroke of the last sketch as the first stroke of the next sketch, creating this recursive drawing machine with the same architecture. Similarly, we used here another machine learning framework to train a model on site. This requires no training, where you could train it in 5 minutes to recognize certain gestures and to be able to drive the robot with these gestures, which some of our workshop participants turned into this system that could accept human guidance, human guidance, to build things in real time. Or this other system where the participants use the system to automate the tedious process of like moving slip on a mold, but also customizing some of the orientation of that mold. And lastly, I would like to present this project that I did last summer. It was a speculation on sculpture and art, and so what we did was we grabbed this boulder that was like, it was a really beautiful marble boulder that was like abandoned on the river. We used the robot to 3D scan it, and then we used some genetic algorithms to propagate a maze pattern on top of it. But what's interesting about this project is that even though the final milling process was offline, what I did was I used the real-time capacity of the system to use a simulation environment, that one, and then to simulate everything beforehand in real time and figure out what were the areas where the robot was not going to be able to reach, what was out of bounds, and then heuristically clean that up from the previous model. So I used real time for simulation instead of for the final object, which is what I did represent here. So I use these case studies. I'm going to wrap it up, 5 minutes. I'm going to wrap it up here. I use these case studies to showcase that beyond the offline model, there's another world that is possible. And there's another world where like this richness of interaction between elements, modules, and this modular approach to creating programs is possible because systematically, the technical core that is a problem is already figured. And then interfacing with it externally all of a sudden becomes really easy. And also, these projects represent 3 things that I'm interested in, which is the fact that these projects were implemented by a whole variety of people with a whole variety of different skills, from complete novel people to super users. These projects were driven by very different agents, so from humans to machine learning to deterministic algorithms. And these projects were implemented in very different varieties of concurrency, right? From like the very, very real-time back and forth data exchange to a more paused, turn-based, I send a lot of stuff, I get information back, I make decisions, and then I set a lot of batch, to the very offline paradigm, which is a very slow form of real-time. You send everything, and then you just never listen anything back, all right? And I'm going to conclude this presentation with the user study that we did to prove the other assertion that I made in this dissertation, which is approaching robots in this way is much easier to learn than with other systems. So we were set up to compare this, but what could we compare these to? So we chose universal robots, which are branded as one of the most user-friendly robots that you can find on the market right now. They're very popular, all right? And we set ourselves to compare how users learned and did robotics, comparing it with from Machina to universal robots. So participants in the study were taught how to use robots with a set of standard training from Universal Robots. It's the UR Academy. You can go online. And then I created a set of tutorials to use Machina, similar in content, similar in scope, and similar in duration for a fair comparison, right? And then after users were trained in Universal Robots and in Machina, with one of them, for each system, they were asked to implement 2 basic tasks. One was just drawing a square on a paper with a marker, and the other one was to pick up this object here with these grippers that were on the robot and place it on top of this platform here, all right? 2 very simple, very standard operations that you can find very commonly, all right? The study was designed as a crossover study where half the participants were started training with Universal Robots, the other half did Machina, and then there were surveys all over, and then after they finished the group, they went to the other system. That was designed that way so that the analysis of the data could be done on the first half, where there's no bias, people have not been exposed to anything else, but also it could be done so that at the end, they can compare the 2 systems between them, all right? And it was such an interesting experience. So interesting. I had never done real user studies. I recommend. It's tedious, it takes forever, but it's really interesting. The demographics we had 20 participants. The demographics are something that I can show here. Most of them had 3D printed stuff before. Only 3 of them have used robots. It was interesting to have some people that were not purely novel, but had some exposure to robots before. They were fairly acquainted with the typical design tools that we use, and some of them were good with coding, but mostly it was not the main platform. And the results were very favorable. So altogether, people found in general Machina easier to use, easier to learn. It provided a more fluid experience, and all these sorts of things. I commend you look at the data on the dissertation. There's a lot of numbers, but basically, it was interesting that people, at first, they all liked both systems the same, but once they tried the other system, people liked Machina much better than the other one, after comparison, all right? Interestingly, they found Machina much easier to use in general than Polyscope. Participants were way more engaged during the training than they were during Polyscope because they had a tool that allowed them to type things and do things while they were learning, instead of having to go back and forth from the training. They found that testing things on the physical robot while learning was way, way better for understanding the system than on the other way. And participants were measured how much time it took them to complete each one of the tasks. They didn't know that. I was doing that secretly to avoid bias, all right? And implementing the square task was way faster with Machina than it was with Polyscope. However, finishing times were very comparable when it came to the pick and place operation. That is because the Universal Robots have this thing where you can actually drag the robot, move it around, and program the robot that way, which is an incredible affordance. Again, an object to think and interact with, right? Which I could not mimic on the digital side. So because picking up and placing involved these complex rotations, it was much easier to implement by dragging the robot around than implementing that with rotations. But yet, completion time were still comparable here, all right? However, people found much easier for both tasks to be implemented with Machina, all right? Here, what you can see is the results of the squares. On the left columns, this column, these are Machina implementations, and on the right-hand side, you have Universal Robots implementations, all right? And altogether, comparatively, in general, people found much easier, much more intuitive, and much nicer to use Machina. Yeah, again, you can look at the data. Task A, the square, much a killer, but for the other task, it was comparable. Again, still Machina was leading, but the free drive option was much more. But what's interesting is like not only the good things, but what I learned from this process. And what I learned is that people thought that, again, Machina was easy, intuitive, et cetera, et cetera. But what was not great was, for example, the syntax. People found consistently that moving between relative and absolute motion was very confusing. And a lot of the deal about that was the syntax, was the fact that all the actions have the same name, but if you add the to suffix, then you change the mode, right? People found that consistently confusing, and it's probably bad design from my side, all right? So that's something that needs further work. People didn't feel very safe, because since they didn't know really the effect of what an action was going to be, sometimes they felt something was going to go wrong. So they wanted the system to prevent them from doing erroneous actions, which has like a lot of subjective thinking behind. And also, people complained generally that the system did not provide enough feedback. They didn't know what the coordinate system was. They didn't know what was going to happen when the action was executed. So an enhanced feedback system was necessary here. The good things about Polyscope was that the free drive option was amazing, and that it felt safe, because as you're moving the robot, you know that that's where it's going to go on the final program, right? However, people complain consistently about the clunky interface, which is really surprising for like the easiest to use robot. They very surprisingly found that it was impossible to enter precise coordinates, and I will get to that back in a second. And just as with Machina, they also wanted a higher level of feedback from the system. Yeah.
We kind of wrap up. Okay.
Okay. So a lot of failures, a lot of broken tools, mostly of Machina. This is what I mean by entering precise actions, and I found a lot of sketching and but it was a really interesting experience altogether. And what I think has value is that consistently, whenever every single user finished implementing successfully a task, again, this smile about accomplishment and happiness, right? And yeah, I'm going to conclude here. So I presented today Enactive Robotics, this model for concurrent machine control. I defended that it's easier to learn, that it provides a deeper set of possibilities. I presented the conceptual model, some technical implementations to back it, and I presented case studies and a user study to back those sessions, all right? There is a lot of work to be done yet. There is how we have to prove how this model can be extended to more than just industrial robotic arms. There is the question of increased feedback. There is the question of like providing feedback about the future of the actions before they actually happen. And there's also the question of safety, because industrial robotics arms are dangerous. So pre-embedding enhanced safety in the system is definitely something that should be worked upon. All right? And before I conclude, I want to do a round of acknowledgements and thank yous. I would like to thank my advisor, Professor Martin Bechhol, my advisor, Professor Michelatos, and my advisor, Professor Mueller, for the guidance, for the support. This would not have been possible without them. And if there's any scholarly work on this, it's definitely their fault, not mine. I would like to acknowledge my research group. They have an incredible support, physically and mentally, all through this time. I would like to thank each and every one of the participants in the control user study for their patience. I would like to thank especially all the community in the form of workshops and people who have worked with the environment and who have been patient enough to deal with all the bugs and all the problems that were in this experimental endeavor. And I would like to thank my friends, my family, and my partner for their support, which is invaluable and is obviously, I cannot express how grateful I am. I would like to have a special mention for Autodesk. Their support has been critical. The work of my colleagues at the generative design team, the incredible team at the build space, the leadership that I have been with. I am very thankful that they believed in this project and that they supported it. And I would like to conclude that I believe all of this work from the very beginning, no matter how much I've talked about the robots and machines, but at the end of the day, all of this work has always and is always been about humans and about people. I believe that in a future where the conversation is so dominated by how machine learning and robots are going to take over all of our jobs and render all of us useless, making machines and closer to people and providing better access to them is critical to bring these two worlds together in a world where we're going to need these machines, and we're going to have to live together. So going towards human-robot collaboration, I think, is part of this endeavor. And I will look forward to a future where this example that I showed before, the one describing Peak, is not a story of failure, but is instead a story of success. A story of success because the tools that we use to drive robots and program them situate humans at the very center of those systems, and therefore human-robot collaboration is not a fancy fad word in conferences, but it's a practical fact nowadays. And that's it. Thank you very much.